Hello students, one more prerequisite to perform the RC circuit is we need to understand the theory behind this RC circuit. In our experiment we are going to understand the discharging behavior of the capacitor, and hence let us try to see the theory behind discharging of a capacitor. So we are going to understand discharging of a capacitor. To understand this, let us take the circuit diagram which we are going to use in our experiment. The circuit diagram consisting of a battery followed by a key, and this battery will be connected to the given capacitor. So this is the positive terminal of the battery, this is the negative terminal, and hence this is positive and this is negative of the capacitor. Now what we are going to do is, in this experiment, we are going to close this key. This is known as key. When we close this key, the charge is going to be enter into the capacitor, and hence the capacitor will be charged. For example, the capacitor is charged from 0 to Q0 during charging. Once the capacitor is charged to the maximum value, what we are going to do is, we are going to open the key. So for charging, we need to close the key, and for discharging, we need to open the key. But when the key is open, the circuit is now not closed. So what happens is, the charge will not flow in a open circuit. So for that purpose, what we are doing is, we are going to discharge this capacitor through a resistor. For example, this is R and this is C. This is battery B. So while discharging, what we are doing is, we are measuring the charge flow and using a device called galvanometer. For example, this is positive and this is negative. So when we open this circuit, what happens is, the charge will be discharged from the capacitor through the resistor and the galvanometer, and during discharging, this galvanometer actually measures the charge flow. That means during discharging, the charge is going to decrease from the maximum already which is present, that is Q0, to, let us say, minimum value, some minimum value. Now here, let us try to understand the behavior of the discharging of a capacitor. In general, the behavior of the capacitor during discharging is given by Q is equal to Q0 e power minus t by RC. Here Q0 is the maximum charge that is already present in the capacitor, which is acquired due to the charging, which we are not considering here. And during discharging, what happens is, initially the charge is at Q0, and as time goes on, this charge is going to decrease and come to minimum. And there is a time called time constant, which is in general represented by tau, and mathematically it is given by tau is equal to R into C. You can ask, sir, why we are taking the product of these two, why not the sum or subtraction or division? Because we need to maintain the dimensional equality on both the sides. That means the dimensionality of this particular time constant and the product of RC are same. The dimensions are same. So we are taking the product. For the dimensional purpose only we are taking the product. Now, if you want to understand qualitatively about this time constant, initially the charge is Q naught, which is present in the capacitor. During discharging, what happens is at t is equal to RC, we are calling it as time constant, which is known as tau. At t is equal to RC, that means RC is some value, which is also time. We are calling it as time constant. Okay, now at t is equal to RC, what is happening to our charge? Q is equal to Q naught e power minus t means RC. RC by RC means 1. That means what you will get is here Q naught by E. That means at t is equal to RC, our charge is becoming Q naught by E. That means physically what we can understand is Q naught is the maximum charge that is present in the capacitor and it is decreasing during discharging process, and at particular time t is equal to RC, this Q naught is becoming Q naught by E. So this particular time we are calling it as time constant. That means it is the time required for a capacitor to discharge its maximum charge from Q naught to Q naught by E is known as the time constant, mathematically given by R into C. So in this particular experiment, we are going to understand the time constant of a given RC circuit. That means we are going to determine, first thing is we are going to determine the time constant tau is equal to R into C. This is a theoretical value and we are going to verify it with experimental value. That means experimentally we are going to measure the time constant. Let us see how do we measure experimentally this time constant. For measuring experimentally, what we are going to do is, during discharging behavior, we are going to measure the charge as a function of time. For example, this is the table that we are going to consider in the experiment, and here I have taken time and this is, let us say, charge, or we can also consider this as deflections of galvanometer or deflections in G galvanometer. Now initially at t is equal to 0 second, the charge which is present in the capacitor will be shown in the galvanometer, that is, let us say, for example, 25. And as time goes on, after 5 seconds, let us say this time is in seconds, 5 seconds, 10 seconds and so on, what happens is this value is going to decrease. So we are going to measure the deflections in the galvanometer as a function of time, and then we are going to plot a graph for deflections in galvanometer versus time. So in time in seconds, this will be something like this. Look at this, it will be like this, exponential decay curve we will be getting. So they are all actually the data points. For example, we are considering these are the data points. Initially the maximum charge that is present at t is equal to 0 second is given as Q naught. That is how much in this particular case? Q naught is 25. Now we know that the time constant means R into C. This is the theoretical value, but experimentally what we understand just now is the time required for Q naught to become Q naught by E. Q naught by A is known as time constant. So from this curve, calculate Q naught by A. Q naught is 25. 25 by A, you can calculate how much you are getting. For example, you got some x value here. So on this y-axis, you identify that x value, whatever it is. And corresponding to this x-axis, corresponding to this x value, you can draw a horizontal line which will be intersecting your curve at a particular point, and draw a vertical line from that particular point, and it will be intersecting your x-axis, which is actually time, at particular value, which is we are calling it as the time constant. For example, here you will get the value. This is actually the time constant measured experimentally. So the time constant that we got here through experiment and the time constant that we can calculate from theory has to be matched. This is what we are going to do in this experiment using the simple circuit which we have just now seen. So this is about the theory behind this particular experiment. Thank you.